On the morning of January 28, 1986, spaceflight changed forever. There is a time before and a time after Challenger. No other disaster has shaped modern spaceflight like the tragic loss of Space Shuttle Challenger and her crew of 7. The events leading up to this fatal day and the lessons learned are essential for the safety standards we find today across spaceflight and the entire aerospace industry. But despite all of this, the true story of what really happened on January 28, 1986 is still unknown to many. Hey there, what's up and welcome back to the Rocket Hub. My name is Philip and today I will be your guide through a chain of events that led to the Challenger disaster. This may be one of my most extensive videos to date, but that is warranted as I believe that knowing the full story of Challenger can drastically change our approach to certain decisions in our own lives by learning from the mistakes of others. The version of the story of Challenger that most people, apart from the few that have actually conducted some research into the accident on their own, are familiar with is that of the infamous broken O-ring. And while essentially correct, it is what the official accident report lists as the primary cause of the accident after all, it is far from the whole story. The really interesting and in some ways shocking part isn't how a single piece of rubber was able to bring down the mighty space shuttle, but rather how that piece of rubber was allowed to be on the shuttle in the first place. This video roughly follows the timeline of events that led to Challenger's destruction in chronological order, which in my opinion is the easiest way of understanding these events. Should you, as a viewer, not be too familiar with the technological details of the space shuttle, don't worry. Every necessary detail will be explained once it becomes relevant. So, with all of that said, let's go back in time to the very beginning of the chain of events that led to the tragic loss of Challenger. To understand the events that occurred on the fateful winter morning of January 28, 1986, we have to go back in time, 9 more years in fact, to 1977. The story of the Challenger disaster really begins inside a company called Molten Thiokol, based in Wasatch, Utah. Engineers of the company had been busy for about 3 years designing the solid rocket boosters, or SRBs, for the upcoming Space Transportation System, the launch vehicle consisting of 2 of said boosters, an external main tank, and the Space Shuttle orbiter itself. These SRBs, as designed by Molten Thiokol, consisted of 4 distinct segments, which were all connected by Tang and Clevis design field joints, which all possessed a complex seal to prevent hot exhaust gases leaking out from inside the booster. Central to this joint design was a set of 2 O-rings, hollow tube-like rings made from a fluorocarbon rubber material that were positioned between the 2 parts of this specific joint design. Once the SRB was started and hot exhaust gas let the hull of the SRB expand, these O-rings would create an airtight seal that would withstand the exhaust gases pressing against it from the inside. At least, that was the plan. As early as 1977, NASA engineers of Marshall Space Flight Center had noticed that this seal design had a series of major flaws. In a test conducted by Molten Thiokol earlier that year, the engineers measured a pretty large rotation of the segments, meaning that excessive horizontal movement between the individual parts of the joint was possible. Don't get me wrong, this movement was still just marginally larger than 1 millimeter, but that was enough for the joint to flex, which allowed the O-ring seal to be weakened enough for hot exhaust gases to erode and escape the seal. NASA engineers suggested a change to fix this problem using so-called shims to keep the O-rings at their designated position and stop larger rotation from occurring, but they never received an answer to this suggestion. While it is unclear why exactly these objections were ignored, there's some evidence pointing towards Thiokol never even receiving any of NASA's written letters in which these objections were made clear. The first safety barrier was crossed and the issue remained unfixed. But that was far from the only issue with those double O-ring sealed joints. Around the same time the rotation issue became visible, the NASA Verification and Certification Committee requested further testing of those flawed field joints, including temperature tests from 4 to 32 degrees Celsius. These tests were meant to verify the seal integrity across a wider range of possible launch conditions than the earlier defined limits, which only verified seal integrity above 12 degrees. A similar test at slightly different conditions had shown that low temperature-induced changes to material characteristics led to unsatisfactory results. More tests were seen as necessary by the committee. However, the higher-up program directors of MSFC decided that these tests were not necessary and therefore were not to be conducted. The only thing that was done was an updated critical items list, with the O-rings being reclassified from 1R, meaning they were able to cause a complete mission failure, therefore classified as Class 1, but being redundant as indicated by the R due to a secondary ring being present, to Class 1, as both thermal integrity as well as the by then known rotation issue did not guarantee O-ring redundancy. The first case of O-rings in the SRB field joints losing integrity and failing occurred on just the second flight of the shuttle ever conducted, STS-2, in November 1981. Soot and hot exhaust gases had managed to erode the primary O-ring and intruded into the space between the two rings, but did not get past the secondary ring. On the launch of STS-51D during the winter 1 year before the accident, the first case of temperature-induced O-ring erosion was recorded. At an external temperature of 17 degrees Celsius, the primary O-rings of multiple joints had been eroded substantially, but did hold the seal, even if only barely. These issues went so far that Thiokol did in fact order a redesign of these joints, but decided to continue using the old design until the new ones would be ready in the mid to late 1980s. Thiokol had noticed the issues with the design, but did not believe they were impactful enough to require a grounding of the entire space shuttle fleet. All this led to two major issues, both of which known to certain NASA divisions and engineers at Thiokol, being present on the solid rocket boosters mounted to the external fuel tank of the STS-51L carrier rocket, which was scheduled to launch Challenger on January 28, 1986. Mission STS-51L was originally scheduled to launch in July of 1985, but the launch had to be delayed multiple times due to payload changes and weather and slipped all the way into late January 1986. The mission was to be flown and executed by OV-099 Challenger, the second of originally 4 Space Shuttle orbiters, completed back in 1982. Prior to Mission 51L, Challenger had successfully flown 9 operational missions. Mission objective of 51L was, along with a series of onboard scientific experiments, the deployment of 2 satellites. The Tracking and Data Relay Satellite B, abbreviated as TDRS-B, on top of an inertial upper stage, a small rocket booster to be fired in orbit to bring the satellite to its final position in geostationary orbit, and the Spartan satellite, a small observation satellite that was to be deployed, observe Halley's Comet as it passed close to the Sun, and later be retrieved again by Challenger. Challenger's crew for 51L consisted of 7 trained NASA astronauts. Mission Commander Francis Richard Scooby, Pilot Michael John Smith, Mission Specialist Alison Shoji Onizuka, Judith Aline Resnick, and Ronald Irvin McNair, as well as payload specialists Gregory Bruce Jarvis and Sharon Krista McAuliffe. Out of these 7, 4 had previously been to space on board the Space Shuttle, while the other 3 had never been to space before. 2 members of the crew somewhat differed from the rest, as both Jarvis and McAuliffe weren't career astronauts. Jarvis had been selected as one of 2 engineers of the U.S. Aircraft Corporation to become astronauts to conduct a series of tests of new aerospace designs in a zero-G environment. McAuliffe, on the other hand, was a teacher who had been selected for the Teacher in Space project and was supposed to give 2 lessons from space to her students. All 7 crew members completed standard astronaut training provided by NASA and were declared ready for the mission. After multiple pushbacks, the launch of STS-51L had been scheduled for a 9:38 a.m. liftoff time on January 28, 1986 from pad LC-39B at Kennedy Space Center, Florida. In the days and especially the last night leading up to the launch, temperatures had been unusually cold for the region, dropping well below zero, making these the coldest conditions a shuttle launch had ever been conducted in. This information about the expected weather only arose days before launch. However, the O-ring problem involving cold temperatures was known at the time, just not to everyone involved. On January 15th, the SRB pair was officially certified for the mission and no mention of the possible failure was made. And this somehow continued right until the day before launch, January 27th, 1986. Originally, STS-51L was supposed to lift off on that day, but launch was postponed due to violent upper-level winds, and Challenger remained on the pad overnight, exposing it to the cold. Since the timeline of the events will become a whole lot tighter now, the exact time of events will from now on be given in Eastern Standard Time, or EST, as this is the time zone used at Kennedy Space Center. Due to the forecast temperature, a meeting of NASA's mission management team was held around 2 p.m. They were concerned about the cold, but decided only to activate the orbiter's heaters and did nothing about the SRBs, which would be fully exposed. Until now, less than 24 hours before the accident, it appeared that nobody knew about the O-ring issue at all, or at least wasn't made aware of its full extent. The first concerns arose about an hour before this meeting, at around 1 p.m., in a conversation between NASA manager Lawrence Ware and his Thiokol counterpart Boyd Brinton, both of the SRB program. Having heard about the temperature forecast, Ware had asked Brinton about what effects Thiokol, the manufacturer, expected on the boosters, as he remembered one of the earlier mentioned incidents where temperature-induced O-ring erosion had occurred. Brinton subsequently called another manager at Thiokol, relaying Ware's question. The evaluation of possible effects the cold might have on the SRBs was then tasked to a group of Thiokol engineers, among which was one Robert Eberling, ignition systems engineer, assembly manager and SRB expert at Thiokol. A meeting of this group occurred at 2:30 p.m., in which everyone agreed that the cold may pose a serious problem, as the expected temperatures were way below what the SRBs had been certified or ever tested for. The engineers possessed no data that would ensure them the O-ring would work, but the previous operational incidents demonstrated to them that they almost certainly would not form a proper seal. This was then communicated to the SRB program manager Alan J. McDonald, and the concerns of Eberling's team were brought forward to Carver Kennedy, NASA's director of VAB operations, at around 4 p.m., who then relayed an updated weather report back to Eberling. At around 5:15 p.m., McDonald then also called the Marshall Flight and Research Center KSC chair manager Cecil Houston and informed the latter about the concerns brought forward by Ebeling, who then immediately set up a meeting with both Marshall staff and Thiokol engineers to further discuss the matter. This meeting is then held as a teleconference around 5:54 p.m., involving personnel from Thiokol as well as Kennedy and Marshall Space Centers. While the possibility of pushing the launch back a few hours to allow the temperatures to climb is discussed and multiple members agreeing on this being the right way forward, no immediate action is taken, apart from scheduling a second conference at 8:45 p.m. It is also suggested that more data should be exchanged to further evaluate the problem, and more people are requested to be present at the later conference. Shortly after this meeting, another call is held between two of its attendees, Stanley Reinhardt at Kennedy and Judson Lovingood at Marshall, both managers of Marshall's Shuttle Project Office, in which Lovingood recommends not to launch should Thiokol's concerns prove to be correct. At around 7 p.m., Reinhardt meets up with Lawrence Malloy, SRB Program Manager at MSFC, who had also participated in the first teleconference. The two men then visit Marshall Spaceflight Center Director Dr. William Lucas and Jim Kingsbury, Director of Science and Engineering, in their motel rooms to inform them about the ongoing situation and the meeting later in the day. By this point, quite a lot of people were aware of the issue and working on a solution, including people from the highest level of authority inside NASA. At 8:45 p.m., just as planned, the second teleconference begins. In this meeting, data is presented by various Thiokol engineers suggesting that temperature-induced O-ring erosion is likely to occur during the predicted conditions of the STS-51L launch window. Based on this data, Morton Thiokol's Vice President of Engineering, Robert Lund, recommends to the present NASA personnel to delay the launch of Challenger until an O-ring temperature of 53 degrees Fahrenheit or 11.7 degrees Celsius can be guaranteed, as this was the lowest temperature in which the O-rings of the SRBs were proven to function properly, as demonstrated on earlier flights. After being asked on his opinion by Malloy, Joe Kilminster, Vice President of Space Booster Programs at Thiokol, agrees with Lund and also recommends delaying the launch. Despite multiple people advocating for a delay, some of them are opposed to the idea and do not share Thiokol's concern. One of them was Reinhardt, who commented on believing the lower boundary of the temperature window the SRBs were certified to work in to be 40 degrees Fahrenheit or just 4.5 degrees Celsius. However, this claim was heavily disputed by the other meeting members. At around 10:30, the teleconference was temporarily disbanded to allow for more discussion in smaller groups and more information gathering. In this break, two separate groups form. At Kennedy Space Center, Malloy, Reinhardt, McDonald and Houston engage in a discussion, in which McDonald especially challenges Reinhardt's claim about the certification temperature range and further argues in favor of a launch delay. However, it becomes clear that the other attendees of the separate meeting, mainly Malloy, didn't want to delay the already long overdue STS-51L mission any further. He and Reinhardt were adamant in their opinion to launch and tried to pressure McDonald into arguing in favor of launching, although the latter would not give in. At the same time, over at the Wasatch plant of Thiokol, a similar caucus was held. In this conference, a heated argument over whether the launch should be recommended or not ensues. Multiple key people, including Lund, Ebeling, Rocket Motor Cases Division Supervisor Arnold Thompson, and SEAL Task Force member Roger Beaujolais, a close friend of Ebeling, argue in favor of a delay since they are convinced the O-ring issue may prove fatal to the crew. Due to the discussion involving at least 14 people, no consensus could be reached and a management-only round was formed to make a decision. This final round included Kilminster, Lund, Wasatch Operations Vice President Gerald Mason and Space Division General Manager Kelvin Wiggins. They came to the agreement that their final decision should be. Even though primary O-ring erosion could occur, they are convinced the secondary O-ring will close the seal even in low-temperature environments. Since data on the effects of cold temperatures on the O-rings is inconclusive, vehicle management decides to recommend the launch of Challenger. While things aren't clear, and I certainly don't want to blame single individuals for this decision, it is most likely that while Lund was against recommending the launch, Kilminster, Wiggins and Mason were in favor. When the teleconference continued at around 11 p.m, Kilminster informs the other members of the conference of Thiokol's decision, reads a rationale and will soon after fax a written recommendation in favor of launch to both Marshall and Kennedy spaceflight centers, which is signed personally by himself. Soon after, the meeting is dissolved. Between 11:15 and 11:30 p.m, the discussion between the smaller KSC group continues, with McDonald attempting to halt the launch one last time, disillusioned with NASA rationalizing launching below the qualification temperature of the SRBs. McDonald once again argues in favor of a delay, citing the O-ring concerns, believing them to be a critical issue, and openly speaks out about him not wanting to take responsibility before a board of inquiry in case anything went wrong. His concerns were ignored, and he's told by Reinhardt, Malloy and a couple other key NASA figures that these shouldn't be his concerns, but those of the ones above him. This was the final time anyone tried to stop the launch from happening, as everybody that held some sort of authority over the launch process from this point was either handed the recommendation by Thiokol or not even informed at all. Despite the best efforts of multiple people, especially Alan MacDonald, Robert Ebeling and Roger Beaujolais, the go for launch would be given. Between 11:30 p.m. and 12 o'clock a.m., Reinhardt and Malloy joined in a phone call with Arnold Aldrich, manager of the National Space System Program Office at Johnson Space Center, talking about various other complications coming up before launch, including positioning of the recovery vessels in rough waters. The O-ring concerns are never brought up. Aldrich remains completely unaware. The separate meetings at Marshall, Kennedy and Thiokol slowly break up, and their attendees try to catch the little sleep they might get this night. It is now January 28th, 1986. Between 5 and 8 o'clock in the morning, various people are informed about the events of the last night, including Dr. William Lucas and Jack Lee, Deputy Director of MSFC. Both are shown the fax signed by Kilminster recommending launch and therefore are not concerned about the O-ring issue. In the final hours before launch, ice crews at Launch Complex 39B report ice present on the boosters. The temperatures measured on the outside of the right SRB's hull are down to negative 13 degrees Celsius, far beyond the point at which O-ring failure can occur. The ice crews, however, are not concerned, as they too remain completely unaware of the issue. At some point later this morning, Robert Ebeling drives from his home back to the Wasatch facility together with his daughter to watch the launch from there. According to her, Ebeling was convinced his Challenger was going to blow up and everyone on board would not survive this morning. They were later joined by Beaujolais, who shared the exact same belief until the very end. 11:38 a.m. Eastern Standard Time. Challenger is launched.
7, 6, we have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Despite everything that occurred prior, the countdown clock is never stopped. Mission STS-51L proceeds on schedule. From 11:37 a.m. and 53 seconds onwards, the three main engines of Challenger are ignited. Only 6 seconds later, the ignition command is sent to both SRBs. The two massive boosters ignite in an instant, marking the moment of T-0. There is no more turning back now. From now on, all events will be referred to using the time elapsed since T-0, 11:38 am. In the exact moment the right SRB is ignited, the O-rings form a seal under normal conditions. However, due to the cold temperatures that morning, the two O-rings inside the right aft field joint had shrunk beyond acceptable levels and enabled hot exhaust gases to blow past them through the gap formed and the entire field joint. As this happened, both the primary and secondary O-ring in the right SRB aft field joint failed. At roughly 0.6 to 1 second after liftoff, multiple puffs of grey smoke can be seen exiting the field joint between the 280 and 320 degrees positions, which is where the failure occurred, near one of the aft struts that connects the SRB to the external main tank, which is positioned at 310 degrees. At 3.375 seconds, all indications of problems are gone. There is no more smoke coming from the SRB, and to everyone on the ground, the launch looks completely normal. At this point, not a single person in mission control is aware that any of this has happened. Except for a handful of people, none of them even knew about the concerns regarding O-ring failures or had seen the fax issued during the last night. In the following seconds, Challenger successfully completes the scheduled roll program. For anyone on board or on the ground, everything still seems fine. Due to the way solid rocket motors work, there's a thick layer of unburned solid fuel present on the inside of the broken seal, with some of it having traveled inside the seal and plugged it. For now, only small amounts of exhaust gas are able to escape the field joint, not posing much of a threat for the rest of the vehicle. The only indication available to mission control was a single pressure sensor inside the right-hand SRB displaying a pressure reading 11.06 psi higher than normal. While unusual, this indication in isolation, without everything else that we know in hindsight, would not be of any serious concern to anyone on the ground. Mission Control had no reason to be concerned about a higher than normal pressure reading, as nobody expected a failure in the SRBs, and a sensor failure was far more likely. Therefore, the issue went completely unnoticed. At around T+36 seconds, Challenger reaches a layer of high winds, blowing it off course. Automatic yaw and roll response systems are able to correct these movements by gimbaling Challenger's main engines and using her control surfaces. However, the experienced forces are enough to initiate the final chain of events leading to disaster. Only 40 seconds into the flight, just after Challenger has reached supersonic speed, the solid fuel plug that had formed in front of the seal and prevented most of the exhaust plume from exiting the right SRB is dislodged by the rapid acceleration caused by wind shear and the automatic response to it. There is now nothing left preventing hot exhaust gases from inside the SRB from escaping. 58.788 seconds into the flight, a flame begins to appear near the faulty field joint exiting the right SRB. This flame cannot be seen by anyone in this moment, as the cameras recording it aren't transmitting live pictures to mission control. Only a few milliseconds later, Challenger accelerates through max Q, and the three main engines are throttled up to 104% thrust, the maximum setting. Following at T+59.272 seconds, the flame begins to grow, the field joint slowly being eaten away by the hot exhaust gases shooting out the side of the SRB. From 60.238 seconds onward, a growing pressure difference between the two SRBs is observed, the right one having now developed a sizable leak, while the left one is perfectly fine. Only 10 milliseconds later, the flame is seen attaching to the main frame of the external main tank, being forced towards it by the air rushing by the vehicle. It only takes little more than 4 seconds for the hot plume to burn through the isolating layers around the external main tank. In the vicinity of ring frame number 2058, located right next to the damaged field joint, the tank springs a leak, and indications of liquid hydrogen joining into the anomalous plume are observed. A bright glow can be seen on the sides of the external tank as hydrogen flows out. 64.937 seconds into the flight, the plume has grown large enough to influence the aerodynamic forces on the vehicle, and the gimbal systems of Challenger's main engines begin to move to cancel out these forces. The plume begins to cause transient motion of the entire vehicle, pushing it towards the left. Over the next few seconds, the hydrogen leak begins to grow dramatically. At T plus 66.764 seconds, sensors pick up major deviations in ullage gas pressures inside the liquid hydrogen tank, caused by unusually large amounts of liquid and gaseous hydrogen exiting the tank. Between 68 and 70 seconds into flight, the last transmission between Challenger's crew and mission control takes place. It is a routine call-out regarding their flight profile.
Engine now at 104%. Challenger, go and throttle up.
Challenger, go and throttle up.
Finally, after having been exposed to the hot plume coming from the broken field joint for over 14 seconds, the right SRB's aft connector strut attaching the booster to the external tank structure frame fails at T plus 72.204 seconds. The right SRB is now only attached to the rest of the vehicle at the top, allowing it to swing freely. Subsequently, the pitch and yaw rates of the two boosters begin to diverge rapidly. Because of this, the vehicle experiences lateral acceleration in positive y direction of up to 0.227 Gs higher than normal. Both the three main engines on Challenger and the nozzles of the two SRBs are reoriented to account for this motion, but the flight computers ordering these motions from the respective actuators are fighting a war they cannot win as the right-hand SRB swings regularly. Meanwhile, pressure inside the liquid hydrogen tank has dropped significantly, and the three main engines are receiving decreased fuel flow, forcing more oxygen to be injected into the combustion chambers to keep delivering full thrust. At T plus 73.124 seconds, the pressure inside the right SRB has dropped a full 19 psi below that of the left booster, giving an idea of just how big the hole originating from the broken O-rings had grown. At the very same moment, the bottom structure of the external hydrogen tank fails. A white cloud emerging from the bottom of the external main tank indicates the severity of this failure, as tons upon tons of liquid hydrogen rush out the tank, emptying it rapidly. At T plus 73.143 seconds, all three main engines record a loss of fuel, and the maximum available oxygen flow rate is no longer enough to account for it. And then, the inevitable happens. At T plus 73.126 seconds, the right SRB slams into the lower structure of the external main tank. The collision causes a bright flash, which is visible on ground cameras. With the booster, which is still running, slamming into the hydrogen tank, the structure of said tank is thrusted upwards, colliding into the liquid oxygen tank, which in turn fails catastrophically. Dozens of tons of liquid oxygen exit the external main tank, mixing with the hydrogen pouring from the liquid hydrogen tank. The two fluids accumulate in the space between the orbiter and the remains of the external tank. All three main engines initiate shutdown as both fuel and oxidizer sources are lost. T plus 73.327 seconds. The gases pouring out from the external tank come into contact with the intense heat from the still running engines and sparks from the collision. With an abundance of oxygen available, the hydrogen ignites. T plus 73 1.618 seconds. Challenger explodes. Both the orbiter and the external main tank disintegrate into countless pieces, while the two SRBs stay largely intact, powering on into the sky. Although hard to believe, it is likely that at this point all 7 crew members are still alive. Challenger's cockpit did in fact survive the explosion mostly intact, with all 7 astronauts still inside. We believe that all 7 were still alive at this point because a couple switches had been moved to unusual positions and a couple personal egress air packs had been activated, which indicates that at least some of them must even have been conscious. The cockpit, having been completely detached from the rest of the orbiter and without any ability to control itself, entered a ballistic trajectory, reaching an apogee of 65,000 feet only 25 seconds after the explosion. From then on, the crew of Challenger, trapped inside their cockpit, were free falling towards the ocean. It is not fully known when exactly the cockpit impacted the surface of the Atlantic Ocean, but it has been determined that the impact happened at a velocity of around 333 km an hour, resulting in impact forces exceeding 200 Gs. While unconfirmed, it is possible that some crew members kept consciousness all the way down to impact. Nonetheless, the impact with the ocean itself was later deemed an unsurvivable event. All 7 crew members were instantly killed by blunt force trauma. 110 seconds after liftoff, more than 45 seconds after the explosion had occurred, the 2 SRBs of Challenger, which had actually remained intact and had been continuously flying on random trajectories following the accident, were finally terminated through activation of the flight termination system. This marks the last event of the accident sequence. Immediately following the accident, the 2 NASA SRB recovery vessels Liberty Star and Freedom Star were dispatched for mission control for initial search and rescue operations. However, it quickly became obvious that the mission had become a recovery effort. The 2 NASA vessels were in the following days joined by several US Navy vessels and submarines, as well as commercial recovery ships. Until January 31st, the search effort had expanded to include 16 ships and several military scouting aircraft. On the evening of the disaster, United States President Ronald Reagan, who had originally been scheduled to give his yearly State of the Union address that day, postponed his speech and instead spoke to the nation about the accident on the evening of January 28th. A memorial service at which he was present was held at Johnson Space Center only 3 days later. Following the accident, the failure of a field joint on one of the SRBs was immediately considered one of a few likely scenarios which could have caused the accident, given the suspicious amount of indications of the night before. The theory became increasingly likely as footage of ground-based cameras was analyzed and a plume exiting the right SRB was discovered. On the 1st of March, the remains of the damaged field joint were located on the sea floor and successfully recovered on April 13th. The Presidential Commission tasked with figuring out the reasons for the disaster, better known as the Rogers Commission, was formed on February 6, 1986. Led by Chairman William P. Rogers, the commission included many prominent people of the aerospace sector, among them being Neil Armstrong, the first man to walk on the moon, Sally Ride, the first American woman to fly to space, famous physicist and Nobel Prize winner Richard Feynman, and aviation legend Chuck Yeager. The commission released its final accident report on June 6, 1986, confirming the O-ring failure as the primary cause of the accident. NASA implemented multiple design changes on both the solid rocket boosters and the orbiters themselves following the accident, aimed at improving safety and reliability of the shuttle. Starting in 1987, the construction of a new fifth orbiter was undertaken and completed in 1990. This fifth orbiter would act as Challenger's replacement and would later be named Endeavour. After almost 2.5 years, the Space Shuttle returned to flight on September 29, 1988, with Discovery launching for the STS-26 mission. Until April 15, 1986, the bodies of all 7 crew members were discovered and brought to the surface. The bodies were transferred to Dover Air Force Base, where another memorial service was held with the caskets of the 7 astronauts on April 29th, before being handed over to the families of the 7 crew members. Scobie and Smith were both buried at the Arlington National Cemetery, Onizuka at the National Cemetery of Honolulu. McNair received his own memorial park at his hometown of Lake City, South Carolina, where he rests until today. McAuliffe was also buried in her hometown of Concord, New Hampshire. Finally, both Resnick and Jarvis were cremated and their ashes spread among the seas. Several memorials have been erected across the country, including at Kennedy Space Center. In memory of the lost astronauts, a crater on the dark side of the moon and an asteroid were dedicated to each crew member, carrying their names in their official catalog designations. Since the Challenger disaster, 40 years have passed. In fact, should you be watching this video the day it was released, then today marks the 40th anniversary of the accident. In the time since, much has been learned. Starting with the accident report of the Rogers Commission, many things changed. Among the recommendations issued by the Commission based on their investigation were massive design changes to the field joints vehicle used on their boosters. A new joint design had to pass a series of extensive tests to fully understand and evaluate, among other criteria, the possible movement margins of such joints and especially the impact of environmental factors on the joint. Furthermore, the Commission's recommendations required these tests to be overseen by an independent board to make sure these changes actually happened. The management structure of the Space Shuttle program was also recommended to be a subject of reconsideration, as mismanagement and perceived power structures led to excessive pressure being felt at both Marshall Space Flight Center and Thiokol, something that shouldn't be necessary if the organizational structure of the Space Shuttle program had been more centralized. Therefore, the Commission recommended a reviewed management structure to avoid similar cultural developments in the future. The Commission also issued a recommendation in favor of a full review of criticality and hazard analysis evaluations for all parts on the shuttle system. This includes every single mechanical, electrical or other component along with the software needed to control them. As the redundancy and criticality in case of failure of the O-rings had been misevaluated multiple times, this review was meant to identify and solve similar issues and misevaluations that might exist for other parts of the orbiter, boosters or the external tank structure. This review as well had to be led by an independent commission that reported directly to the administrator of NASA. Another recommendation concerning the management errors in the prelude of the Challenger disaster was the establishment of a shuttle safety office, reporting directly to the administrator of NASA. Said office would be tasked with the supervision of safety checks, reliability assessments, and quality assurance of all NASA departments, making sure no corners are cut and issues do not go unnoticed. One recommendation was directed specifically at Marshall Space Flight Center and their communication with NASA management after failing to report on the critical O-ring issue they had known about for years. The Commission urged NASA to root out this behavior through structural as well as personnel changes, as well as requiring MSSC to record all meetings held and share these recordings with NASA management. The final few recommendations issued were all directed at improving general issues with the shuttle program not directly related to the accident. These included improvements to landing safety on future shuttle missions, more possible crew escape scenarios, a reduction of shuttle flight rate to allow for more safety checks and less time pressure, as well as introducing additional maintenance safeguards. All of these recommendations were aimed at improving flight safety of NASA missions and guarantee refined organization and management structures once the shuttle returned to flight. Although the Commission heavily criticized NASA for their failures, these recommendations were seen as an adequate way to prevent similar shortcomings in the future. Normally, this would be where the accident report would end, after citing all sorts of sources and documents, of course. However, that isn't the case with the Rogers report. Right at the end of the report, on pages that aren't even included in the publicly available version, we find Appendix F. Appendix F was written by Robert Feynman, who kind of went rogue during the investigation. He felt that the Commission was investigating into the wrong direction and that the real cause for the accident lied way deeper within NASA. And what he found is quite interesting. Other than the rest of the Commission, Feynman fully blames NASA management for the accident. According to Appendix F, there was a massive disparity in safety assessments between management and engineers, with managers repeatedly claiming the chances of a fatal accident occurring being 1 in 100,000 or 1 accident in 300 years when flying every day. At the same time, engineers working on a space shuttle seem to agree on a way lower number of around 1 in 100. And as it would turn out, even that was too optimistic, with the real value being 1 in 67.5. This drastic disconnect came along with widespread miscommunication, false claims, safety test results that just didn't make sense at all, and most shockingly, blatant misinterpretation of industry safety standards and misuse of connected terms. For example, NASA management claimed the O-rings had a safety factor of 3, which would normally mean they could endure 3 times the stress they had to, when in reality they would burn through 1/3 of the thickness when used. Feynman was, rightly so, disturbed by things like these, which is openly apparent in his report. The whole investigation, which only took around half a year, uncovered many glaring holes within NASA's management and safety structures, overconfidence in their own machinery, and many more issues that needed immediate fixing, much of them extending far beyond the O-rings and thiacol. Both the official accident report and the somewhat independent Appendix F outline NASA's shortcomings in these areas and their origins quite well, and therefore are really worth the read should you be interested in learning even more about the dynamics that led to the Challenger disaster. When I started my research into the Challenger disaster in preparation for making this video, I knew little about what actually happened in the last 24 hours before launch. But now, after getting pretty familiar with the chain of events as outlined in this video, I am more confused than before. Challenger's demise was an accident that was more than just avoidable. In fact, it is somewhat shocking and even enraging to know that what cost the lives of 7 astronauts was an issue that had been known for almost a decade and yet had somehow made its way onto Challenger's carrier rocket. Not only have there been documents found that confirmed that NASA and especially MSFC staff did know about the O-ring issues way before the accident, they did as early as 1977. Yeah, NASA and thiacol knew about these issues a full 9 years before the accident. That is 4 years before the maiden flight of the Space Shuttle. And the issue was widely known among thiacol engineers, and some had been issuing reports and warnings to the management for years. Even some of the key people involved in making the decision to launch Challenger had been made aware of these issues months or even years ahead of the accident. Robert Lund, the vice president of engineering at Malta Thiokol that was directly involved in making the final decision, had known of the severity of this issue since at least July 1985, when Beaujolais raised his concern about the O-ring issue to Thiokol management, including Lund, Boyd Brinton and Alan MacDonald. After O-ring erosion had occurred on STS-51B, he wanted to make sure that management is fully aware of the seriousness of the current O-ring erosion problem in the SRM joints from an engineering perspective, and criticized Thiokol's lack of action to correct this issue after knowing about it for years. At this point in time, Beaujolais was well aware of what could happen in certain conditions and was afraid that inaction of Thiokol's management might lead to a loss of life in the future, and as it would turn out, rightfully so. In fact, he was so familiar with the O-ring issues that, in the same memo, he managed to predict almost the exact failure mode that would occur on Mission 51L half a year later. But despite dozens of warnings like this one from Beaujolais, the issue went completely ignored. In fact, it seems like the SEAL team assigned to solving the issue was hindered in their work and delayed by all means. On purpose. Yes, that is a bold claim, but it isn't mine, it's Eberling's, as he stated in an inter-office memo addressed once again at Thiokol management from October 1985. The phrase, "we do not know how to lead development program," is kind of frightening knowing where this leads. A lot was going wrong inside Thiokol at the time. Even some of the people that actively tried not to postpone the launch by a single minute had been made aware of the seriousness of the issue and still didn't do anything about it. For example, Lawrence Malloy, who adamantly urged other teleconference members to recommend launching and showed what one could call disrespectful behavior towards MacDonald, who of course opposed him, had known about these severe issues with the O-rings as early as September of 1985. It's almost ridiculous just how many people in mentioned positions at both Thiokol and Marshall Space Flight Center had been made aware of these issues and their potential consequences months or even years before the accident. And yet, nobody tried to fix the issue, despite dozens of engineers telling them to do exactly that. They simply didn't listen to them. Management knew that further delays could cost the company money and that NASA was growing impatient. After all, they were nowhere near their annual flight goals, and STS-51L was already more than half a year behind schedule. Therefore, any further design changes to the SRBs would have meant more delays and costs that the agency simply couldn't afford. NASA had been under immense pressure from, well, themselves, having set themselves goals that simply weren't achievable, and that pressure was felt at Thiokol as well, especially for their managers. In the end, the entire accident can be put down to one of the far too many cases of safety being put second and profit first. And that only happened since, as per usual, the people in charge made their own decisions, despite resistance from those that knew better. This mentality has caused many catastrophes in the past, particularly in the aerospace sector. But not listening to those that do know better and ignoring safety issues for potential profit are things most of us have done in our own lives as well. Risk evaluation and risk-based decision-making are things most of us still have to learn, especially if we are in a position in which we are responsible for the lives of others. And that is the case way more often than we think. NASA has learned this lesson the hard way, but something similar has luckily never happened again. Since Challenger, there have only been 2 fatal spaceflight accidents in the Western world, and at least the demise of Challenger's sister ship Columbia in 2003 was put down to different issues, although the demise of Columbia had been influenced by the remnants of pre-Challenger operations at NASA, as this accident was a result of unfixed safety issues as well. But in Columbia's case, the errors made weren't nearly as bad as with Challenger. Today, should blatant safety issues be found on a crewed vehicle, a mandatory delay is needed to correct the issue. Had these regulations been in place all the way back in 1986, the Challenger disaster would probably never have happened. But as so often, not everyone has learned the same lesson, as the other fatal crash since 1986, that of Virgin Galactic's Spaceship Two VSS Enterprise, was also caused mainly by lacking safety standards and negligence, and company culture similar to that at Thiokol in the 1980s played a significant role in the recent scandals involving Boeing. On a personal note, it is quite upsetting to see how easily this particular accident could have been avoided. The issue was widely known, and enough data existed for at least some people involved to be fully aware of the issue's full extent. Yet, any action to prevent the disaster from happening wasn't taken, or even sabotaged to accelerate progress and avoid costly delays. It was mostly corporate greed on both sides, NASA and Thiokol, that ended up taking 7 lives. Well, obviously, I wasn't there in 1986, and therefore my knowledge is limited to the official accident report and all those Senate hearings of people involved, so I'm not really in a position to point fingers at people and blame them for killing Challenger's crew. But some of the actions taken by certain people leave me wondering what on earth they were thinking. They simply wanted to launch on that morning, no matter what, and in order to do so, ignored every single safety concern that might arise. Confirmation bias and blissing ignorance are things that shouldn't have a place in engineering, and Challenger's demise is the perfect example as to why that is. In the end, the tragic death of 7 astronauts on board of Challenger, as avoidable as it might have been, has made spaceflight far safer than it ever was. But carrying their legacy and making sure the lessons learned from the Challenger disaster are applied today and in the future, that is fully up to us now. If you are seeing this, I want to thank you for watching this video until the very end. I've been working on this particular one for well over a year now, and I really appreciate your support. If you enjoyed this video, consider dropping a like and subscribing to the Rocket Tub for more future content. We'll see ourselves in the next video, and until then, I'm out. Cheers!